Hello everyone. Today I'd like to present you my project, EEE573 project, about MRI T1 to PET and MRI T1 to T2 image synthesis using Pix2Pix GAN, which is a conditional generative adversarial network. So here are the motivations of this project. Why should we synthesize a PET image, positron emission tomography image, from an MRI image? If the patient is healthy, that we know the patient is healthy, if we generate PET images from his or her MRI images, then we can reduce the radiation exposure that the patient gets, and for the hospital, the cost of tracers are reduced. Moreover, more importantly, we can obtain a healthy baseline for the PET image. So if we can compare it with an diagnosed or to be diagnosed PET image that has some risk of being diseased, especially Alzheimer's disease or epilepsy, we can subtract those images and localize the problematic tissues, problematic areas in the PET image. And as an addition, I'd like to introduce the motivation to go from T1 to T2 MRI, which is basically if we have one pulse sequence, let's say focusing on T1, we should be able to generate the other pulse sequence output, which would be focusing on the T2 relaxation. So they would essentially show different things. And the goal here is to use a conditional GAN, Pix2Pix, to learn these distributions and transformations and to go from one modality to another. As per the dataset, I would like to introduce it as PET MRI pairs. They have been obtained from Bilkent Retina Vision and Learning Group. They contain MAC FDG 30 sharp PET images, T1 Bravo MRI images, T2 Cube MRI images. These are T1 and T2 respectively MRI images. And for all of these three modalities, we have 23 healthy training groups, 4 healthy validation groups, and 9 healthy test groups. Additionally, we have 10 Alzheimer's disease test groups, which don't contain T2Q, but they do contain both the PET and the T1 MRI. And as I said, these are purely for testing purposes because we want to generate a healthy baseline. So we don't put them in the training groups. We use only for tests, basically. And we have 89 actual slices per subject. They are 16-bit grayscale. There may be occasional PET MRI pairing mismatches that are smaller, strictly smaller than 1 millimeter in terms of the depth in a longitudinal fashion. So they are quite minimal. So here's a sample data set, so to speak. Slices from a data set. They are corresponding, they are from the same patient. This is PET image, this is T1 MRI image, and this is T2 MRI image, basically. Next up, we have the Pix2Pix GAN. Let's describe it as a method. We have a generator unit. It contains encoder and decoder structures. It has skip connections within. We have a discriminator, which is a patch GAN, and it classifies local patches or as real or fake. And it's useful because it doesn't focus on all of the image at once, but rather it focuses on small patches of the image, which is useful. And moreover, here's the training loss objective, basically a combination of adversarial loss from GAN and the reconstruction loss to see how well we reconstructed the synthetic output to resemble the ground truth. We train for 200 epochs for both of the sessions in both MRI-to-PET and T1-to-T2 sessions. On an NVIDIA RTX 4090, they took 5 to 6 hours each of them, around 10 to 12 hours in total. And I have given the references for the paper and GitHub code in this presentation and in the report. So here are my evaluation metrics. PSNR is basically peak signal to noise ratio, a commonly used metric in electrical engineering. SSIM is structural similarity index. It's ranging from 0 to 1, and 1 means structurally alike. You can use it to test how well the synthetic images resemble their original counterparts. And LPIPS is a similar used metric as SSIM, but it uses a pre-trained network like VGG on performing in more, let's say, a depth analysis in feature level. And we then have qualitative visual inspection, which means we subtract synthetic and real images and take the absolute value. And as you'll see, these will be quite important when we go to the results section. So here is a demonstration. If we want to clone the repository, we can just put the website link clone it as I did. Then we run the training script. We also open up the wisdom server, and then the training script is opened like this. It's printing the parameters, and we have epoch numbers logging out, and in the wisdom server we can see MRI to PET conversion has started, and the losses are plotted like this, and the checkpoints, as I trained it earlier, go like this, and it should stop at 200 as such. And here is the T1 to T2 training, a similar procedure again. And as you can see, the T1 to T2 conversion has begun. These images, these slices are basically in the middle inferences to observe how the training goes, and here are the checkpoints. As for the testing, we do a similar procedure. Here we test MRI-to-PET, and as you can see, it will log on. It's using the latest generators checkpoint from the folder that I just showed you. And for some sample images, the testing is complete. And for now, we are doing the inference or test for T1 to T2 MRI. And it's again taking a similar procedure. We are using a different checkpoint, of course, and a different data set for inference. And it's done like this. Here are the sample images, the test images. These are for the Alzheimer's disease cases, and these are for the T1 to T2 slices, as you can see them. Okay, so here are my qualitative results. This is T1, original T1 MRI, this is original PET, this is the synthetic PET. When you subtract these two, as you can see, almost a complete black screen with minor details are obtained, which means we have indeed got a similar synthetic PET compared to the original synthetic PET. This is for the healthy case. And these two patients are diagnosed with Alzheimer's disease. So, as you can see, these areas called the parietal lobes in the left and right lower corners of the brain have lower activity than usual. And this is the healthy baseline PET, synthetic PET, obtained from the MRI. And when you subtract these two, you obtain the abnormal areas, which means these areas have high difference. And this indicates that these regions in the original PET have some problems compared to the healthy baseline, which actually showed a quite good result for this case. And for this patient, we apply a similar procedure, but there are some other, as you can see, noise-like subtraction outputs. This is because for some slices like this, the MRI and PET don't align completely well. There's a small rotation mismatch, which means there are all the other things here, but still this area has hypometabolism, the lower corner, and in the lower left corner of the difference image also shows it, which is good. And these are the qualitative results for T1 to T2, and as you can see, the subtraction images almost show nothing but small edge-like details, which means we have managed to generate very good replicas. Here are the quantitative results for the aforementioned metrics. Basically, in summary, this means that healthy dataset outperforms the Alzheimer's disease dataset in MRI-to-PET, which is expected because we have done the training on the healthy dataset. And here we have T1 to T2 translation. We don't have the Alzheimer's disease test case because, as I said, we don't have T2 data for the Alzheimer's disease patients, so nothing to compare them with, basically. So that part cannot be done like that. I've just explained the findings, and the limitations are the minor misalignments, which causes artifacts and also noise-like structures, and the GAN training also fluctuates a lot, especially in the T1 to T2 case. So here are my references. Thank you for your attention.